Hi, and welcome back to Dr. Brown Codes. I'm your host, Dr. Brown. Today, in this episode, I'm going to go over the session that I have at the 2025 ASHI Annual Meeting. So in Workshop 5, I'm the speaker for Bioinformatics of Running the HLA Lab. It's not for the faint of heart. I'm going to be giving a talk on mismatching. My colleague Rayut Had-Dvorai is going to be giving a talk on informatics for PT testing. And then I'm going to give another talk where I actually show how to run some code. So on the website here, it has some information to learn more. Please click here. And if you do that, that's not what I meant to do. I think what I actually meant to do, let's try that again, is to prepare for this session, complete the following steps, click here. All right, when we do that, it gives a link to a online web service called Posit Cloud. So I'm going to click on this link here. It is going to send me here to Posit Cloud. Posit Cloud is a great way that it has something much like RStudio in the cloud, and so you can upload and run some code that way. So when you first log into this, if you don't already have an account, it will ask you to sign up. I already have an account, so I'm going to click login here. And when I do that, and when you sign in, you should see here, it comes up with the 2025 ASHI Annual Meeting site. And then the actual content for today is here, using ImageNetter for HLA data analysis. So if we click on that, it'll take a few minutes while the website loads the project here. And so we can wait for that. All right, great. When the website has loaded itself and loaded everything you need here, you can see something that looks very similar to RStudio. And when you open it up, if you don't see something up here that says workshopcode.qmd, what you can do is go down to this page over here, click on the workshopcode.qmd, and this will bring up what's called a Quarto document. Quarto document is just a way that you can have notes for yourself and then have these code chunks, as they're called. And we can see these code chunks are between these three backticks here. So I have written this so that you can follow along just what's written. I'm obviously not going to read everything today since we're going through this together. But if you want to go back and do this on your own, you can go and read through any of these things. So the first thing you'll have to do here is install two packages that are needed for this. ImageNetter is the package that I've co-developed. Tidyverse is another package there. If you just click on this green Run button over here, it will install those. I'm not going to do that because I've already installed this. That's only something you have to do once. But then after that, what you can do is actually load those two packages, and so I'm going to do that here. When I click on that, it doesn't show any output because I've already loaded these, but you should see something indicating that you have successfully loaded it. All right, great. Now let's actually get into some coding here. So today I'm going to be going over the functions for mismatching and matching, and we're going to start with a function that's called HLA mismatch logical. This is the simplest of all of the mismatch functions, and it was designed to tell you if a mismatch exists or not. In order to get these mismatch functions to work, you need to have the typing of the recipient and the donor in a GL string format. And so here I've put in a really basic GL string. The recipient type here is HLA-0201 plus HLA-A06801. This is a GL string format. The plus separates two alleles at a locus. And so you can see here that we are assigning this to recipient type. And then donor type is going to be homozygous for A0201, and we are assigning this to donor type down here. So now the way the function works, this HLA mismatch logical function, is it takes four parameters. The first is the GL string of the recipient, and here you can see that is the recipient type that we just defined up here. The next is GL string of the donor, which you can see is the donor type that we just defined up here. The next is loci. We have to tell the function which loci we want to perform typing at. And obviously we only have put in HLA-A typing here, so HLA-A is the locus we want to do. And then finally we have to say what direction we want the mismatch function to operate on. And of course that's going to be host versus graft, graft versus host, or bidirectional. So here we can see we've set it up for host versus graft. If we do that, we can go up here and press the run to run this chunk. and you can see it gives an output of false. And so we can go and double check, make sure that's true. So we look in the host versus graft, and so that means the recipient is looking at the graft and seeing if there's anything that it would recognize as non-self. And of course it doesn't. This A0201 is in the host, so it wouldn't be that way. But of course we can play around with this a bit. We can go to graft versus host. We can go back up here, click run, and we can do that. You can see it shows an output of true. There is a mismatch in the graft, the donor looking at the recipient. And we can clearly see here that the HLA A06801 would be the mismatch there. We can try some other things. Another way we have this written in here is you can do SOT for solid organ transplant. If we go and run on that, you can see it gives a false. Solid organ transplant is really just the same as host versus graft, but then we can also do bidirectional. And when we try that, you can see it gives a true. Bidirectional really just means, are there any mismatches in either the host versus graft or the graft versus host direction? And so we can see here that this mismatch logical function has lots of different ways that we can set things up and get different results. All right, let's try this with a different function that's related to it. It's called HLA mismatch alleles. And as the name implies, now instead of giving a true or false output, it's going to tell us which alleles are mismatched, if any of them are. So we have another recipient type defined up here, donor type defined down here. The actually setting up the function here is going to look very similar. We have our recipient type, our donor type, our loci, our direction. There's a new setting in here, which is homozygous count, which basically is saying if a genotype is homozygous, do we want to count the mismatch 1 time or 2 times? All right, so here we have it set up for counting it 1 time, and so let's see what happens when we do that. All right, so here we're looking at the solid organ transplant, which would be the host versus graft direction. We should see exactly the same thing when we do that. Sure enough, it's the same output down here. And it's saying, all right, if we look at the host, which would be the recipient looking at the donor, the graft, it is seeing 1 mismatch, HLA0201 there. But what happens if we were to set this as 2? Well, now it gives us 2. The HLA0201 is doubled. The idea here is when we set the homozygous count equals 2, we're saying that we realize that there are 2 alleles at every locus, and so we want those 2 alleles to be output there. And of course, we can look lots of different ways here. We can do host versus graft, and when we do that, I'm sorry, I think I meant to do graft versus host, and when we do that, we should see now that it's giving A0301 and A6801 as output. And of course, now if we change this to 1, this should not change anything because this is not a homozygous locus and there's going to be no difference there. Whatever we put in the homozygous count there is not going to matter. All right, perfect. Let's move on. This time we're going to do the mismatch number function. And as you can imagine now, instead of actually giving the alleles that are mismatched, this time it's just going to count the number of mismatches at every locus. So here we've put recipient type in as a homozygous, or donor type in is also homozygous. And if we go down here, we can see that the setup is very the same. We have to give an input of GL string recipient, the donor, the locus we want to perform matching at, the direction we want to do it, and now the homozygous count, either 1 or 2. So if we run this, we can see this is giving an output of 2. It is saying in the solid organ transplant, which is the host versus graft direction, there are 2 mismatches there because we set this up. If we set this up as 1, now we should see that this changes to 1 because we have a homozygous mismatch here, and we're saying only count that homozygous as 1 mismatch. All right, great. So lots of different functions here. All right, so one of the other things that I wanted to show is, we've been using just very basic genotypes here, but I wanted to show something that's going to look a little bit closer to what you would see in a clinical laboratory. So luckily Immunogenetor, the package that I developed, has some sample data in it. Here we were going to look at a piece of sample data called HLA typing LIS. If we click on run here, because this is in parentheses, you can see that it automatically shows us the table. And so here we have a table, and we can see here pretty clearly that this table has HLA typing. And the difference here from what we've been doing before is this is not a GL string. Instead, we have one locus for each column, right? MA1CD.recipient is the first A typing, MA2DC recipient is the second A typing, right? So we can see 0201 and 2402 are the two alleles for the A locus. And using this black arrow here, we can scroll through and we can see that we have typing at pretty much all of the classical HLA loci for this report. All right, so if we wanted to perform mismatching on something like this, we would first need to get this into GL string format. So luckily, Immunogenetor has a very nice function that will do that for us. It is called HLA columns to GL string. All right, so there's a lot going on here. Maybe I'll make it just a little bit smaller so we can see. But we are taking this HLA typing LIS, which is what we're just showing up here. We're going to make a new table that we're calling HLA typing LIS GLS strings here. We're going to pass a mutate function to that, meaning that we want to make a new column. And in that column, we're going to call the column GL string, and we're going to fill that column with data from the HLA columns to GL string function. And this is a function that will take all of these commons and automatically turn it into a GL string. And when we're doing that, there's a couple of settings that we have to set up for that. This period there is actually a fairly important setting, that it's saying the data that we want to use for this is coming from the table that we're working on. The next is you have to tell it which HLA typing columns you want. And so we're saying here we want every single column from MA1CD.recipient through MDPB1CD.recipient. Then the next thing is that the way this function works, it tries to figure out what locus it is based on the name of the column, right? So it's going to try to figure out, we want to get it to figure out that this is the A locus, and this would be the B locus, this would be the C locus, etc. To do that, we have to tell it to remove some of the prefixes. So here we can remove the M because that will get us to A, and at the end we can remove the CD.recipient because that will get us down to A1 and A2. So the locus plus a number for the two alleles there. All right, so here we're saying prefix to remove is M, suffix to remove is CD.recipient, and then finally we're saying that we want this column, this new column that we're going to call GL string, to go after patient. All right, so that was kind of complicated to set it up, but let's see what happens when we do that. All right, so this has now made a new data frame down here, a new table for us. And you can see now we still have the same patient. And in the next column is the GL string. And so each one of these GL strings now is the full HLA genotype of this individual. And we can see here this is the original data that was used to make this GL string down there. All right, now this is great because now we have full genotypes in GL strings, and so we can use that to do some really interesting things. All right, so what we're going to do down here finally is we're going to take one of these GL strings from a patient up here, and we're going to call this one of our candidates. So we're going to take this HLA typing LIS GL strings that we just made. We're going to filter for patient number 3, and then we're going to pull that GL string, that typing there. The next thing that we're going to do is we're going to take all of the donors in here, all of the patients up here, and we're going to consider those potential donors. So what we're going to do here is we're going to take that same thing, we're going to assign it to a new thing that we're calling donors. We're going to just select the columns that has the patient number in it and the GL string, and then we're going to rename the patient, and we're actually going to call it donor, just so that we can have something that says donor on it. And then finally, we're going to join these together, and we're going to automatically perform HLA matching like we would do for hematopoietic cell transplantation. So we're going to take this HLA typing, the donor that was up from here, we're going to mutate it, meaning that we're going to put a new column in. We're going to call that column candidate, and we're going to take that, the HLA typing that we got up here for our selected recipient, which was patient number 3. We're then going to mutate and make another column, and this time we're going to call that column match score. And in that column, we're going to fill it with data from HLA match summary HCT. So this is another function from Immunogenetor, and the idea here is this won't automatically calculate matching based as you would do for hematopoietic cell transplantation. All right, and so now the setting for this, the parameters for this function look very similar to what we're doing. We have to tell it where the recipient typing is, and that comes from the column called candidate. We have to tell it where the donor typing is, and that comes from the column called GL string. We have to tell it what direction we want. Here I'm doing bidirectional, which is the way that we perform matching for HCT in the US in general. And then we're going to do match grade, and here we're saying X out of 10. So that's saying that we want to perform matching at the HLA A, B, C, DRB1, and DQB1 loci. Finally, after we get all that done, we're just going to clean up the table a little bit, and we only want to look at the donor type, the match score, and the GL string, and then the candidate. And then finally, we're going to arrange it so the highest match score goes on the top. All right, so we did a lot of setting up there. Let's run this and see what we get. All right, and now we have here donor 3 is the only one that has a match score of 10. And we can see donor 7 and donor 8 have match scores of 1, and then every other donor has a match score of 0. If we wanted to double check this, we could look at the GL string here of the recipient, the candidate. We could look here, I'm sorry, that's the candidate. So this would be the GL string of the donor, and then we could look at the GL string of the candidate, and we can just double check that. But the idea here is that this function is automatically calculating this match score for us. And in fact, the way we set it up is giving us our best match donor at the very top. So this is, of course, going to be something very similar to what NMDP or other registries would do when they're searching for donors. And we have this function in ImageNetter that automatically sets us up. All right, the last thing I wanted to end with for this talk here is I wanted to take a closer look at some DRB1 genotypes. So here we are going to set up a recipient type of HLA DRB1 0101, HLA DRB1 1401, and the donor we're going to have HLA DRB 0101 and HLA DRB 1454. Now this might already raise some eyebrows for some people, but I wanted to show how this is going to work in ImageNetter. So we're going to do the same thing here. We're going to look for HLA mismatched alleles. We're going to take the recipient type, the donor type. There we're going to do the locus of HLA DRB1, and the direction we're going to look at is host versus graft. When we run this, you can see that it is saying that DRB1 is calculating that DRB1 1454 is a mismatch. Now I just want to point out that this is a mismatch simply because these two numbers are real. These two gene names are different. However, many clinical programs might decide that 1454 and 1401 should be actually considered a match because they are in the same P group. And I just wanted to point out that ImageNetter will not automatically do that for you. That is a separate informatics step that would have to be done. When you're doing this, and if you've decided that you want everything within the same P group, for example, or maybe the same G group to be considered matching, you will have to do an extra informatics step there. All right, and that is everything I had here. This is an overview of the talk that I will be giving at the 2025 ASHI Annual Meeting. And thank you everyone for following along, and happy coding.